Hierarchical clustering. What is clustering? To understand what clustering is, let's begin with an applicable example. Let's say you want to travel to 20 places over a period of 4 days. How can you visit them all? We can come to a solution using clustering and grouping the places into 4 sets or clusters. To determine these clusters, places that are nearest to one another are grouped together. The result is 4 clusters based on proximity, allowing you to visit all 20 places within your allotted 4-day period. Clustering is the method of dividing objects into sets that are similar and dissimilar to the objects belonging to another set. There are 2 different types of clustering: hierarchical and partial clustering, each divisible into 2 subsets. The 2 subsets of hierarchical clustering are agglomerative and divisive, and K-means and fuzzy C-means for partial clustering. Every kind of clustering has its own purpose and numerous use cases. First is customer segmentation. In customer segmentation, clustering can help answer the questions: what people belong to together? How do we group them together? Next is social network analysis. User personas are a good use of clustering for social networking analysis. We can look for similarities between people and group them accordingly. Next is city planning. Clustering is popular in the realm of city planning. Planners need to check that an industrial zone isn't near a residential area, or that a commercial zone somehow wound up in the middle of an industrial zone. An example of hierarchical clustering. Hierarchical clustering is separating data into groups based on some measure of similarity, finding a way to measure how they're alike and different, and further narrowing down the data. Let's consider that we have a set of cars and we want to group similar ones together. Look at the image shown below. For starters, we have 4 cars that we can put into 2 clusters of car types, sedan and SUV. Next, we'll bunch the sedans and the SUVs together. For the last step, we can group everything into 1 cluster and finish when we're left with only 1 cluster. Types of hierarchical clustering. Hierarchical clustering is divided into agglomerative and divisive clustering. Agglomerative clustering is known as a bottom-up approach. Consider it as bringing things together as shown, while divisive clustering is known as the top-down approach. We take a large cluster and start dividing it into 2, 3, 4, or more clusters. Next, let us discuss how hierarchical clustering works. Let's consider that we have a few points on a 2D plane with XY coordinates. Here, each data point is a cluster of its own. We want to determine a way to compute the distance between each of these points. For this, we try to find the shortest distance between any 2 data points to form a cluster. Once we find those with the least distance between them, we start grouping them together and forming clusters of multiple points. This is represented in a tree-like structure called a dendrogram. As a result, we have 3 groups: P1, P2, P3, P4, and P5, P6. Similarly, we have 3 dendrograms, as shown below. In the next step, we bring 2 groups together. Now the 2 groups P3, P4 and P5, P6 are all under one dendrogram because they're closer together than the P1, P2 group. This is as shown below. We finish when we're left with 1 cluster and finally bring everything together. What is the distance measure? Distance measure determines the similarity between 2 elements and it influences the shape of the clusters. Some of the ways we can calculate distance measures include Euclidean distance measure, squared Euclidean distance measure, Manhattan distance measure and cosine distance measure. Euclidean distance measure. The most common method to calculate distance measures is to determine the distance between the 2 points. Let's say we have a point P and point Q. The Euclidean distance is the direct straight line distance between the 2 points. The formula for distance between 2 points is shown below. Squared Euclidean distance measurement. This is identical to the Euclidean measurement method, except we don't take the square root at the end. Depending on whether the points are farther apart or closer together, then the difference in distances can be computed faster by using squared Euclidean distance measurement. Manhattan distance measurement. This method is a simple sum of horizontal and vertical components, or the distance between 2 points measured along axes at right angles. Cosine distance measure. The cosine distance similarity measures the angle between the two vectors. As the two vectors separate, the cosine distance becomes greater. This method is similar to the Euclidean distance measure, and you can expect to get similar results with both of them. Let us now take a detailed look at the types of hierarchical clustering, starting with agglomerative clustering. Agglomerate clustering begins with each element as a separate cluster and merges them into larger clusters. There are 3 key questions need to be answered. How do we represent a cluster that has more than one point? How do we determine the nearness of clusters? When do we stop combining clusters? Let's assume that we have 6 data points in a Euclidean space. We're dealing with xy dimensions in such a case. How do we represent a cluster of more than one point? Here, we will make use of centroids, which is the average of its points. Let's first take the points 1.2 and 2.1, and we'll group them together because they're close. For these points, we compute a point in the middle and mark it as 1.5. 1.5. It's the centroid of those 2 points. Next, we measure the other group of points by taking 4.1 and 5.0. We set up a centroid of those 2 points as 4.5, 0.5. Once we have the centroid of the 2 groups, we see that the next closest point to a centroid, 1.5, 1.5, is 0, 0, and group them, computing a new centroid based on those 3 points. The new centroid will be 1, 1. We do the same with the last point, 5, 3, and it computes into the first group. You can see that the dendrogram on the right is growing. Now each of these points is connected. We group them, and finally, we get a centroid of that group, 2, at 4.7, 1.3. Finally, we combine the 2 groups by their centroids and end up with one large group that has its centroid. Usually, we don't compute the last centroid. We just put them all together. There are many approaches you can take to stop combining clusters. Approach 1. Pick several clusters K up front. When we don't want to look at 200 clusters, we pick the K value. We decide the number of clusters, say, the first 6 or 7, required in the beginning, and we finish when we reach the value K. Approach 2. Stop when the next merge would create a cluster with low cohesion. We keep clustering until the next merge of clusters creates a bad cluster setup. Approach 3. Diameter of a cluster. Diameter is the maximum distance between any pair of points in the cluster. We finish when the diameter of a new cluster exceeds the threshold. We don't want the 2 circles or clusters to overlap as that diameter increases. Approach 4. Radius of a cluster. Radius is the maximum distance of a point from the centroid. We finish when the radius of a new cluster exceeds the threshold. Divisive clustering. The divisive clustering approach begins with the whole set composed of all the data points and divides it into smaller clusters. This can be done using a monothetic divisive method. Let's try to understand it by using the example from the agglomerative clustering section above. We consider a space with 6 points in it as we did before. We name each point in the cluster as abgtef. Here, we obtain all possible splits into 2 clusters, as shown. For each split, we can compute cluster sum of squares as shown. Next, we select the cluster with the largest sum of squares. Let's assume that the sum of squared distance is the largest for the third split abgtef. We split the ABC out, and we're left with the def on the other side. We again find this sum of squared distances and split it into clusters, as shown. You can see the hierarchical dendrogram coming down as we start splitting everything apart. It continues to divide until every data point has its node or until we get to K. If we have set a K value, hierarchical clustering applications includes tracking viruses through phylogenetic trees. Viruses such as HIV have high mutation rates, which means the similarity of the DNA sequence of the same virus depends on the time since it was transmitted. This can be used to trace paths of transmission. This method was used as evidence in a court case, wherein the victim's strand of HIV was found to be more similar to the accused patient's strand, compared to a control group. A similar study was also done for finding the animal that gave the humans the SARS virus. Another application is charting evolution through phylogenetic trees. In the decades before DNA sequencing was reliable, the scientists struggled to answer a seemingly simple question: are giant pandas closer to bears or raccoons? Nowadays, we can use DNA sequencing and hierarchical clustering to find the phylogenetic tree of animal evolution, generate the DNA sequences, calculate the edit distance between all sequences, calculate the DNA similarities based on the edit distances, and construct the phylogenetic tree. Thank you.